Okay, so we're going to continue taking notes today, and we're still in Unit 1, our real number system, and now we're going to look at the steps to convert decimals that are non-terminating to fractions. And I know I'm actually going to use two pages there, so I'm going to list this as 5 and 6. So I'm going to go ahead and turn my notebook to page 5. Make sure that it's marked 5. I want to make sure it's marked 6. So steps to convert decimals to fractions, non-terminating. So I'm going to walk through the steps, and then I'm going to show you the proof of why this works. Because in math, that's what we want to know. The proof shows us why something works or how we can explain the justification for something. So the first step is going to be to count the number of digits, or could just be a digit, so digit or digits, in the reptend. Line here. And if you remember, the reptend is what is under the bar notation. These become 9s in the denominator. So with terminating, we counted those numbers behind the decimal, and they became zeros after a 1 in the denominator. Here, there's going to be no 1. There's going to be initially no zeros. It's just going to be 9s based on the reptend. Now I want you to make a special asterisk here that we'll get to at the end. And what I want you to put next to the asterisk is to count the digit or digits not repeating in the decimal. And these become zeros after the 9s in the denominator. Step number 2. Remove the decimal and bar notation and put 1 set of the reptend in the numerator. Again, special asterisk. We're going to say, no, it's going to be the same. Remove the decimal and the bar notation. So remove decimal and bar notation. What's going to change is after that dash. Put the non repeating digit or digits, followed by one set of the reptend in the numerator. In step 3 is the same as what we saw when we're reducing terminating decimals, and that is simplify the fraction. So the asterisk is a special situation. This doesn't happen often. So the special situation is when you have both non-repeating and repeating decimals in the decimal. And I would say digits, I guess. Sorry. Digits in the decimal. So when that happens, you need to follow the special steps that we've outlined with the asterisks. Now, what does that look like symbolically? So symbolically for the purple, it literally would just be the reptend, one set, and number of nines that correspond to the digits. The other side, it's going to be the non-repeats followed by one set of the reptend, number of nines as dictated by the reptend, followed by number of zeros dictated by the non-repeats. Okay, so some examples. Okay, some examples would be if we have 0.12. 0.12. So according, there's no, these are all just part of the reptend. So I go to the purple and it just says count the number of digits in the reptend. These become nines in the denominator. So I have 1, 2. My denominator becomes 99. Second step, remove the decimal and bar notation, put one set of the reptend in the numerator. That becomes 12. Simplify. 12 and 99 have a greatest common factor of 3. So 12 divided by 3 is 4, and 99 divided by 3 is 33. If I have a situation where I have 0.1234, with just the 3, 4 repeating, according to my rules here, I would have to use the green rules. I need to count the digits in the reptand, which are 2, and these become 99s or 9s in the denominator. And then I have 2 that are not repeating, and they become zeros. On top, I take and I remove the bar notation in the decimal. So it becomes 1, 2, 3, 4. And then I want to subtract. So we're going to have to add that up there. I forgot to add that. We want to subtract the non-repeating decimals. So subtract 12. Up here, let's just add in. Then subtract non-repeating repeating digits. So 1,234 minus 12 would equal 1, 2, 2, 2, and I would still have 9,900 in the denominator. And they have a common factor of 2, so that would be 611 over, see, 2 would go in 4, and 2 would go into 19, 9 times, and I split the zeros, so 490. So I can see 7 would probably go into here. 7 definitely wouldn't go into the top. In fact, I can just see that it's not divisible by 3. So that's as far as I can go. 611 over 490. Now let's quickly do the proofs on page 6. So proof, and I'm going to prove 0.12 and 0.1234. So for the proof, I'm going to set the number equal to a variable. So n is going to equal 0.12 bar. And I can actually put more than one set for this. I'm going to put 2. Because the rep 10 is made up of 2 digits, I'm going to multiply both sides by 100. So this becomes 100 n equals 12.12. And I still have the bar notation. Next, again, because this is algebra, I'm going to subtract the same value from both sides. Up here, I said that n and this decimal are equal, which means they're equal values. So I'm going to subtract n and subtract 0.12 into perpetuity. So 100 minus 1 is 99. Bring down my n. Over here, those cancel out, and I'm left with 12. Next, I want to isolate the n by dividing both sides by 99, and n equals 12 over 99. Common factor is 3, so n equals 4 over 33, right? Because as I'm solving equations, as long as I do the same thing to both sides, I maintain equality. Second one, first thing I'm going to do is I'm going to set n equal to my variable, or my variable equal to my decimal. Then I want to get rid of these 2 behind the decimal, so I'm going to multiply both sides by 100. So I get 100n equals 12.34 into perpetuity. Now I have something that looks like where I started over here. Instead of having 1n, though, it's 100n. So I want to get rid of these 2 and behind the decimal, at least a set of the rep 10. So I'm going to multiply both sides again by 100. So I get 10,000 equals 1234.34. Next, instead of going all the way back up to the top, I'm going to go here. And I'm going to minus 100n on one side, and I'm going to subtract 12.34, repeating on the other side. Remember, as long as the value is the same, and I'm doing it to both sides, I'm okay. Here, I see that they're equal, which means they're basically interchangeable. So over here, I wind up with 9,900n, and over here, those cancel out. I'm left with, again, 1,222. And divide both sides by 9,900, 9,900, both sides. I get n equals or 9,900. So again, I'm going to divide both sides by 2. And I get 611. When I divide 9,900 by 2, I get actually 4,950. So you can tell I'm kind of recording this later at night. So over here, I'm going to go back and just change that to 4,950. Is off by just a little bit. Okay, so that is the proof. That's the proof of why those steps work for non-terminating decimals.